All right, welcome everybody. Today we're going to talk about lesson number 30, and this is a brief introduction to chapter 3. Chapter 3 is all about exponential functions and logarithmic functions, and today we're going to start with some really straightforward stuff, reviewing the properties of exponents and then some simple solving of exponential equations. Now, just to be clear, absolutely everything in today's lesson is review, but it's also the places where students most commonly make mistakes. So it, of course, is important to make sure you're writing everything down and asking questions if you have any. So we're going to go ahead and start by reviewing the properties of exponents and then doing some straightforward examples. Notice here that for these six rules of exponents, they are using base A. Depending on what book you're using or depending on what website you're using, you'll sometimes see these with base B or base X. Look at the variables. They're M and N. Sometimes you'll see them as X and Y or all kinds of things. So just make sure you know it doesn't matter what variable is being used. Of course, they are equivalent. So if you have a to the m times a to the n, you're of course going to write it as a to the m plus n, meaning you would add those exponents. So take a look at the example immediately to the right. Because they are both base 5, you're going to go ahead and write your answer as base 5, and then you're going to add up those exponents. So you're going to start by adding up the variables, which would be 2x minus 4x, which would be negative 2x. Add up the constants, plus 2. Now, it's possible that you might stop there and have that be your answer, but you also have another option. The other option is to try to write it so that you don't have a negative in front of that 2x. So what you would do in that instance is you would actually pull in the negative 1 and write it as 5 to the negative 1, which would then become positive 2x minus 2, which means that you could then write your answer as 5 to the negative 1 would, of course, be 1/5, and then to the 2x minus 2. So if you kind of go ahead and compare these two answers, technically they're both correct, and technically they both fit the direction, which says to write it as a single base raised to a single exponent. As we start working through, and depending on the type of question, and of course my directions, you'll be able to kind of tell which of those answers you want to give. But for now, please just make sure you know that they are equivalent. The second rule of exponents, so take a look at number 2, a to the m divided by a to the n. You're going to go ahead and, of course, write that as a subtraction, a to the m minus n. You're going to have to do that in the example that immediately follows to the right, but of course you've got some other work to do first. So notice that before you're going to apply the second rule, you're going to go ahead and do the first rule. So I'm going to go ahead and start by just looking at the numerator. So in the numerator, it's base 2, and I'm going to go ahead and add up those exponents. So that would be 4x plus 4. Similarly, in the denominator, base 2, I'm going to add up all the x's, for which there are 3x of them, and then 1 minus 5 would be negative 4. Then you have base 2 in the numerator and base 2 in the denominator. So you're going to go ahead and subtract those exponents. So your final answer is, of course, going to be base 2. You're going to start by doing the x's. So 4x minus 3x. That would, of course, give you 1x. Then you're going to do positive 4 minus negative 4. 4 minus a negative 4, which, of course, would become a plus 8. So 2 to the x plus 8 would be the answer in this case. Taking a look at rule number 3. So rule number 3, a to the m to the n, you're going to go ahead and multiply those exponents, which is going to give you a to the m times n. So we're going to have to use that property in our example and then use some of the other properties as well. So starting with 2 to the third to the x minus 2, you're going to go ahead and multiply 3 times x minus 2, and don't forget to distribute. So that would be 2 to the 3x minus 6. And then 2 to the 2 minus 2x. You're now back to property number 1, which says you're going to go ahead and add up those exponents. So 3x minus 2x would, of course, give you x. Negative 6 plus 2 would give you a negative 4. So it's actually pretty rare that you wind up only using one of the rules in a given problem. You often wind up using several of them. Number 4, a to the negative n. I need you to understand that that's equivalent to moving the base a to the denominator, and then that would leave you with a positive exponent. So we saw something similar to that in the first example, but just to kind of clarify. So let's say you had 3 to the negative 2x plus 2. You would go ahead and start by thinking of that as 3 to the negative 1, which would give you 2x minus 2, which means you could then write that as 1/3 to the 2x minus 2. Again, as we kind of go through, remember that if you have a base that's greater than 1, that's of course growth. If you have a base between 0 and 1, that's of course decay. So that'll kind of decide whether or not you want to rewrite it as a fraction or whether you want to leave it with a negative exponent. So take a look here at number 5, a to the 0. Hopefully you remember that anything to the 0 power is of course 1. Looking at the example, looks like there's a lot going on there, so perhaps you're wondering how it turns out to be 1. Well, those are kind of the best problems as far as I'm concerned. So taking a look at this example, the first thing you might notice is that we don't have all like bases, which means we need to do a little bit of rewriting. So we're, of course, going to take the 4, and we're going to rewrite that as 2 squared to the 2x plus 2. And then everything else would remain the same, but I'm just going to kind of save myself a little bit of writing here. So I'm, of course, going to go ahead and distribute that. So as I distribute that, that is going to give me 2 to the 4x plus 4. Then I still have 2 to the x minus 1 and 2 to the 5x plus 3. In the numerator, I'm going to go ahead and add up those exponents. So that is going to give me 2 to the 5x plus 3 all over 2 to the 5x plus 3. Of course, you're used to seeing the same thing in the top and bottom and reducing it to be a 1, but just make sure you know why. If you were going to go ahead and use a rule of exponents, you would, of course, do the m minus n, so 5x plus 3 minus 5x plus 3. That would, of course, give you 2 to the 0, and, of course, anything to the 0 power would equal 1. Finally, take a look at number 6. So let's say you had a to the m over n. So that, of course, is a fractional exponent. You would have to remember that that's really equal to the nth root of a to the m power. And again, there are instances where it's preferable to have the fractional exponent versus where it's better to have the index. And then take a look here. Of course, we have a square root of the entire thing. So we are going to have to go ahead and take that into account. And then also notice that we have a base 3 and we have a base 9. You're not allowed to just take the square root of 9. Of course, that's not legal. So we're going to first go ahead and combine things under the radical and then make sure that we apply that radical. So I'm going to go ahead and start by rewriting this as the square root of 3 to the 2x plus 2. And then this would be 3 squared to the x minus 4. That would then become the square root of 3 to the 2x plus 2 times 3 to the 2x minus 8. You're then going to go ahead and underneath the radical, you're going to use the first property of exponents, which says you're going to go ahead and add up. So this would be 3 to the 4x minus 6. Then, of course, when you have a square root, that implies that the index is 2. So you can actually write this as 3 to the 4x minus 6 instead of a square root. That would, of course, be a 1/2 power, which means in your final answer, you're going to distribute that 1/2. So 3 to the 2x minus 3. Let's make that a little more legible. Okay, so that's a review of just the basic rules of exponents, which again, you've seen several times. So make sure that you have them written down and understand relatively easily how to apply them. So if we take a look at our second page here, this is just a bunch of problems asking you to apply the properties of exponents. Again, should be relatively simple and straightforward, but because they are the places where mistakes most typically are made, it certainly doesn't hurt to take a few minutes to go over them. So in your final answer, please make sure that everything has a positive exponent. So for number 1, of course, remind yourself that this is 3 to the 1st, and then x cubed, y to the 5th. These are all powers to a power, which means you're going to multiply. So this becomes 3 cubed, x to the 9th, and y to the 15th. In your final answer, go ahead and actually cube that 3, x to the 9th, y to the 15th. And then remember, typically when you're giving your answers, you usually go alphabetically in terms of the variables, although it really doesn't matter that much. So in number 2, before you can go ahead and combine anything using multiplication, you have to go ahead and use that cube there. And remember, of course, this is 2 to the 1st. So this would turn out to be 3a to the 1st, b squared. This would turn out to be 2 cubed, a to the 6th, and b to the 9th. You're going to multiply. So then 2 to the 3rd is 8 times 3 is 24. add up the a's to the 7th, add up the b's to the 11th. In number 3, 12 divided by 15, please note, so 12 and 15, if you're trying to simplify that of course is not using the rules of exponents. That's just using what you know about reducing fractions. So you're not subtracting them, you're just reducing them. You would of course divide them both by 3, which would give you a 4 on the top and a 5 on the bottom. If you were to subtract those exponents, you would always do the numerator minus the denominator, which would give you a to the negative 2, which means in your final answer, the a squared would have to be on the bottom. As opposed to actually subtracting those exponents, you could kind of ask yourself the question, where are there more a's on the top or bottom, and by how much, which means there's clearly 2 more on the bottom, which is why your a squared winds up in the denominator. In number 4, you can either square everything and then simplify, or simplify and then square everything. So it's really kind of up to you. Let's say we go ahead and square everything first. That's going to give us 3 squared, and then a to the 4th, b to the 6th, over 5 squared, a squared, b to the 4th. 3 squared is 9. 5 squared is 25. Look at the a's. There's more a's on the top by 2 and more b's on the top by 2 as well. So 9a squared b squared over 25. For number 5, you have a negative exponent. So again, there's lots of different ways you can approach these problems. You can apply the negative and then cube it, or you can kind of apply them at the same time. So we're just going to go ahead and use the property which says you can multiply a power to a power, which makes it x to the negative 6, y to the positive 9, negative 15 for the x, and negative 6 for the y. Again, make sure that you are using the property which says you can go ahead and subtract. So x's, negative 6 minus negative 15 would become x to the positive 9th. For the y's, 9 minus negative 6 would become y to the 15th. Both of those would be positive, and both of them would be in the numerator. So to the 2/3 power, again, you have a couple of different ways that you can apply this. So I'm going to go ahead and start by applying the 3 in the denominator. That 3 is really a 1/3, which is really a cube root. So I could take the cube root of everything that's inside of my parentheses to start. So the cube root of 8 is 2. The cube root of x cubed is x. The cube root of 27 is 3, and the cube root of y to the 6th is y squared. And again, that only applied the 3 in the denominator, so everything technically is still squared. So then square the 2, you get a 4, x squared, over 9, y to the 4th. As I've mentioned a couple of times, there are typically so many different solution paths that you can take for any particular exponent problem that hopefully all end up at the same spot. So you could compare 3 different students' work on an exponent problem, and they might take 3 different routes, but they all should wind up at the same endpoint. So if you think to yourself, I would kind of approach it differently, that's not necessarily wrong as long as you get the same answer and as long as you're using the rules appropriately. So, taking a look here at number 7. Again, I'm going to show you some other techniques here. So in number 7, notice that you have everything inside of the parentheses is a positive exponent where you have a negative 3/2 up in the exponent. So an option that you could do if you want is you can take the negative and you can apply that to everything inside. If you apply just the negative to everything inside, that's going to move everything from the bottom to the top and vice versa. So this would now give you 16a to the 4th over 25 to the positive 3/2. Notice that I just applied the negative. Now I'm going to apply just the 2 in the denominator, which of course means the 1/2 power or the square root. So the square root of 16 would be 4. Square root of a to the 4th would be a squared, and the square root of 25 is 5, and that's all still cubed. If I now go ahead and cube everything, 4 cubed is 64, a to the 6th, and then 5 cubed is 125. And then finally, number 8. So again, lots of different ways you could potentially do this. I'm going to notice that everything inside is to a positive exponent where it's raised to a negative exponent. So I'm going to start by just applying the negative, which means that everything is going to flip-flop. So 125, b to the 3rd over 8a to the 9th, and that's now to the positive 2/3 power. Then again, I'm going to apply just the 3 in the denominator, which is the cube root. So the cube root of 125 would be 5, cube root of b cubed, cube root of 8, and cube root of a cubed. Oops, sorry. Okay. So then from there, I think that should be a to the 9th. Sorry about that. So 125b to the 3rd, and then 8a to the 9th. Okay, so to the positive 2/3. So now if I go ahead and take the cube root, that is going to give me a 5b over 2a cubed, and that's also going to be squared. And then if you square, you get 25b squared over 4a to the 6th. If you're wondering, it's kind of convenient that you've only had things that have, nice perfect cubes. Yeah, it doesn't have to, but it's kind of nice just to kind of see the rules in action. So then now that you've just straight up used the rules of exponents, the next set of problems is asking you to rewrite each as a single exponent. And so same idea, but just some more complicated examples. So number 9, again, notice the fact that you have base 5 and you have base 25. So you have to start by getting them all to the same base. You should always choose the smaller base, which would be 5. So you're going to write that 25 as 5 squared to the 3x plus 2, and then distribute that 3 to the 3x minus 6. This would become 5 to the 6x plus 4, and 5 to the 3x minus 6. And then you would go ahead and add those exponents to get 9x minus 2. And again, it should kind of get faster and easier the more you do. And then for number 10, again, the cube root is the same as the 1/3 power. You can apply that 1/3 at any point in the work. I'm going to go ahead and save it to the end. So I'm going to start by writing the 8 as 2 cubed to the 2x minus 1. So this is going to become the cube root of 2 to the 6x minus 3 over 2 to the 3x minus 6. I'm going to subtract them. So that gives me 2 to the 3x. And then negative 3 minus negative 6 becomes a positive 3. And then I'm going to take the cube root and convert that to a 1/3 exponent. That would ultimately give me 2 to the x plus 1. So the reason why it's so important that you're able to not only apply the rules of exponents, but that you're also able to take a look at something like a 25 and a 5 and an 8 and a 2. So you need that in order to solve exponential equations. So let's go ahead and finish up with a couple of those. So notice in the last page here, rewrite each side as a single exponential expression of the same base, then solve by setting them equal. So this is what I like to refer to as solving with something called like bases. And it basically means that if you have something to a power equaling something to a power on the other side, you're essentially able to get rid of those bases and then just go ahead and solve the exponents. So in number 11, the first thing you would notice is that base 9 and base 27, those are of course not the same. You would need to choose a common base. And again, you should always choose a smaller. Try not to choose a fraction if you can avoid it. So base 3 should hopefully be obvious. So 3 cubed to the x minus 2 equals 3 squared to the 2x plus 5. You would go ahead and distribute. So 3x minus 6 and 4x plus 10. Once you're down to 3 to the something equals 3 to the something, you go ahead and get rid of those somethings. So 3x minus 6 equals 4x plus 10. Put all the x's on one side. So 4x minus 3x is x. Put all the constants on the other, and you're going to get x equals negative 16. Sorry, I kind of ran out of room there a little bit. All right, so in number 12, you have a 1/4, and you also have an 8. So hopefully, the more you do of these especially, you will think of using a common base of 2. So 1/4 can be rewritten as 2 to the negative 2, and that's to the x plus 2, and that would be equal to 2 cubed to the x minus 4. So 2 to the negative 2x minus 4 equals 2 to the 3x minus 12. Now you can go ahead and just set the exponents equal. So 5x, add the 12, 8, x equals 8/5. More often than not, these usually wind up being fractional answers because I don't want you to be able to just guess. Okay, number 13. So again, just be careful here. So you're going to go ahead and write the 4 as a 2 squared to the 2x minus 7. And then that's all technically going to be to the 1/2 power. And then this would be 2 to the 3x minus 3. So you can do it in one step or multiple steps. It's really kind of up to you. So squared times, so 2 times 2x is 4x times 1/2 would be 2x. And then the 2 and the half would cancel, which would give you 2x minus 7. So 2x minus 7 equals 3x minus 3. Put the x's on the right, and you're going to get -4. And finally, the last one that we're going to kind of solve all the way through, number 14. So lots of different bases here. Think about the one that they all share. Make sure you don't pick the 4 because that doesn't work for 8. So you're going to pick base 2. So this would be 2 to the 4th to the x plus 2, 2 to the 3rd, and x minus 1, 2 to the squared to the 3x plus 1. So 2 to the 4x plus 8, 2 to the 3x minus 3. That's, of course, just the left side. Saving myself a step here, so I'm going to go ahead and subtract those. So 4x minus 3x and 8 minus -3. So 2 to the x plus 11 on one side equals 2 to the 6x plus 2 on the other side. X plus 11 equals 6x plus 2. So 9 equals 5x, which means that x equals 9/5. Okay, so then finally, while that is certainly the best way to solve exponential equations, you also want to understand the graphical approach. So let's say that you were asked to solve this given equation right here. Because of the fact that you have base 2 and base 1/2, you can go ahead and do that exactly like the problems above, when we should kind of be old hat at that by now. So 2 to the x plus 3 equals, you would write that as 2 to the -1, which would become 2 to the -x minus 1. You would, of course, set those exponents equal. So 4x equals 2x. Sorry, it's early. Equals -4. And x would equal -2. So that is certainly the best, easiest strategy, but it only works if you have like bases. So to finish us up for the day, look at the one underneath. Let's say you were trying to solve the exponential equation 2 to the x plus 3 equals 3 to the x plus 4 minus 1. You would have no recourse with which to solve this algebraically. There's no possible way to find a like base of 2 and 3, which means your only course of action would be to use the graphing calculator. So in the graphing calculator, you would plug one of the equations into the y1, you would plug the second equation into the y2, you would graph both of the functions on the same set of axes, and then you would find the point of intersection. So essentially, when you're solving each of the problems we just did algebraically, what you're really doing is you're finding graphically where their point of intersection would be. So I know this lesson was a little bit long. I know there were a ton of examples. But again, the sooner we can kind of clear up these common mistakes, I think the easier the rest of the chapter is going to be. So homework 30 is what you're going to work on after this lesson. So thanks very much for tuning in, guys, and we will catch you next time.